Hello everyone, welcome to another Wave-to-Wave webinar as part of our series on automated fiber switching technology and applications. Please have a look at our complete webinar lineup to get the full overview to beneficial impacts of automated fiber switching in various deployment applications. Today we will look at introducing automated fiber switching in a flow-through provisioning and test ecosystem component for fiber to the everything or FTTX deployments. FTTX is a generic term for those technologies which bring fiber a step closer to the subscriber. Staying competitive and guarding long-term profitability are two crucial drivers for telcos. To assure their profitability, telcos must optimize their networks, processes, and procedures, and carefully control both capital and operational expenses, commonly referred to as CapEx and Opex. While choosing products for deployment, telcos must keep in mind the network's total cost of ownership, taking into account not only the network's initial cost, but also future expenses and functionality. Today's webinar will showcase ways telcos can achieve the benefits of decreased test and provisioning times, faster time to revenue, better cash flow management, and deferred capital investments that are more aligned to revenue streams. Next slide, please. We'll start with the discussion on typical FTTX access deployment. Fiber deployment applications consist of various scenarios. In a point-to-point network, laser transmitters in the central office, or CO, are dedicated to individual subscribers. A more popular alternative because of its high performance to price ratio is a passive optical network, or PON. These include fiber to the home, or FTTH, fiber to the building, or FTTB, fiber to the curb, or FTTC, and fiber to the cabinet, or FTTCAB. There are also other common subsets of FTTH, such as FTTN, or fiber to the node, or fiber to the neighborhood, FTTP, fiber to the premises, FTTB, fiber to the basement, etc. The FTTH network will have large fiber counts for accessing as many homes as possible. For instance, reaching a neighborhood of 3,200 homes, an outside plant cable would minimally require 100 fibers, one per 32 homes, based on full utilization of the 1x32 optical splitters used in the outside plant distribution. However, considering take rates, spare fibers, splitter usage, future service offerings, distance from CO, and other unknowns, the number of fibers in the outside plant cable would more likely end up being closer to 1 per 8 homes, or 400 fibers. FTTB typically uses the point-to-point architecture in the outside plant, providing a dedicated fiber to each building or block of buildings. In fact, the percentage of commercial buildings connected to a fiber optic network in the U.S. reached 49.6% in 2016, according to the Vertical Systems Group. FTTC typically pushes fiber 500 to 1,000 feet from the subscriber and typically serve 2 to 8 subscribers, utilizing existing twisted pair outside plant to connect to the customer. Bandwidth is dictated by two factors: DSL technology and copper loop length. ADSL 2, 2+, and 2++ are being used in today's FTTC systems. Due to shorter copper loop lengths in an FTTC network, telcos have improved scalability. Large-scale deployments of FTTC are planned in the future. In FTTCAB, the fiber is terminated at a RT, which is an active device typically located in the basement, communications room, or utility closet. Regardless of fiber lengths, all of these networks can make use of PON technology. In fact, some of today's digital subscriber loop, or DSL, and hybrid fiber coax, or HFC networks also qualify as FTTX networks due to their use of fiber access and PONs. Next slide, please. As the amount of fiber dramatically increases, the importance of properly managing fiber cables becomes a more crucial issue. Telcos use various approaches, including single splits, distributed splits, and centralized splits within the CO. The manner in which fiber cables are connected, terminated, routed, spliced, stored, and handle will directly and substantially impact the FTTX network's performance, stability, and more importantly, its profitability. The capital expense of active equipment accounts for about 1/3 of FTTX deployment costs. In fact, the primary benefit of PONs is that it enables telcos to spread expensive COOLT line card equipment costs across several dozen subscribers. In addition, some incremental costs, such as the customer side ONT device, can be deferred until customers are actually signed up. However, the rigid structure of typical PON architectures impose one strikingly burdensome first cost. As soon as a single subscriber on a given PON is turned up, an expensive OLT line card must be provisioned, and this expense is amortized across actual users of the PON. Experience has shown a typical service penetration rate is only around 33% in overbuild residential applications. Therefore, actual OLT line card costs over the service life is 3 times more than planned on a per home connected basis. Some telcos have responded to these cost inefficiencies by concentrating splitters in the CO. In this architecture, end users are connected to one of many PON splitters co-located in the CO. When the new subscribers sign up for FTTX service, a patch cord is connected to a splitter with an available port. In this manner, splitters can be populated fully before additional OLT line cards purchased and deployed. While concentrating splitters solve the problem of efficient population, it raises other concerns, such as dramatically increasing the number of fibers and patch panels in the CO. Technicians spend a great deal of time identifying the correct fiber, conducting pre-provisioning tests, and running patch cords, all of which drive up Opex. An ideal solution is an automated flow-through provisioning flexibility point for fiber management. Next slide, please. An automated fiber switch product, such as Wave2Wave's Roam line of products, offers dynamic fiber cross-connect capability at layer 1. As you can see, the devices support in-input ports and in-output ports with a cross-connect matrix that defines the connectivity between input and output ports. This type of switch provides significant flexibility, CapEx and OpEx savings. An operation and maintenance software control layer issues cross-connect commands and manages the equipment. The slide shows the AFS system located in a CO and serving multiple PONs. After the telco deploys the network and signs the first subscriber, it provisions an expensive OLT line card in the CO on one of the fibers connected to the AFS. The network manager connects the new customer's distribution fiber to the appropriate splitter via the AFS automatically and remotely. A second subscriber signing up for any of the homes connected to the AFS system can be provisioned on the same OLT line card. In fact, the first 32 new subscribers connected to the AFS system can all be connected to the first OLT line card. Therefore, the carrier can fully populate each OLT line card before investing in an additional line card. Telcos can also use automated fiber switching products to enable zero-touch provisioning, in which they provision new subscribers without sending a technician into the field. ZTP has been implemented successfully for servers and data center switches, and now telcos are driving ZTP for FTTX equipment. In this scenario, carriers pre-connect distribution fiber to the customer location during fiber installation. When a new subscriber is ready to be provisioned, CO or provisioning center-based personnel flow-through connects the splitter via the AFS to the appropriate distribution cable. The operator ships the ONU to the subscriber for self-installation, and the network auto-discovers the ONU as soon as it is connected to the network. Zero-touch provisioning may save substantial costs in high-density scenarios, such as multi-dwelling units or MDUs, where entry rights are often difficult to obtain from landlords. In non-zero touch scenarios, one technician travels to the field to connect the drop cable to the customer premises and install the customer premises equipment. The AFS connect the distribution fiber to the splitter and initiate the CO side testing automatically and remotely. Next slide, please. Integrating the CO co-located splitter architecture with an AFS enables a 100% utilization and controlled pay-as-you-go growth strategy to telcos. Load balancing operations can also be performed to spread high bandwidth use subscribers efficiently across PONs, thereby delaying the need to upgrade to a high bandwidth OLT fabric technology. And when the time comes to upgrade to a higher bandwidth technology, AFS can assist in grooming like users on PONs according to their bandwidth requirements to make the transition easier. It is important to note that such an AFS-enabled PON architecture allows telcos not just to defer OLT costs, but to dramatically decrease CapEx altogether. In addition, subscriber churn can be managed with these same OLT line cards, with canceled subscribers moved remotely from the lit fibers and new subscribers moved on to them. And when the time comes to upgrade to a higher bandwidth technology, automated fiber switching can assist in grooming like users on PONs according to their bandwidth requirements to make the transition easier. It is important to note that AFS products such as Roam allow telcos to defer OLT costs and to dramatically decrease CapEx altogether. For example, based on a 33% penetration rate, when the PON reaches maturity, only 1/3 as many OLT line cards would be required versus using an inflexible pure splitter deployment architecture. Next slide, please. Today, an average of 9 connection points per subscriber are found inside a CO that serves more than 50,000 customers. This large number is due to poor migration planning and poor documentation of existing fiber links for the Day 2 techs. Day 2 technicians spend a great deal of time identifying the correct fiber, conducting pre-provisioning tests and running patch cords, all of which drive up Opex. As a demarcation and flexibility point in the network, AFS also performs 4 basic functions: protection and identification of incoming and outgoing cables, provide a transition point to the outside plant, facilitate moves, adds, and changes, testing and diagnostics, and organization and identification of fiber connections. The dynamics of new FTTX services are constantly evolving, making it difficult to identify the right network architecture. Additional flexibility in splitter placement will allow the telco to get the most out of FTTX, including the ability to use the same fiber access network to take advantage of any service opportunities that may arise, such as next generation wireless carrier front haul network transport. Given this network service flexibility and new business operating models, municipalities and utilities are also looking to get into the FTTX business. Next slide, please. Some municipalities and utilities deploy FTTX networks as an open infrastructure over which multiple service providers can deliver a wide array of services. Typically, these wholesale networks are deployed in point-to-point architectures, facilitating competition by enabling the physical network operator to physically connect the end user to a service provider of choice. Using manual fiber distribution frames to provide physical connectivity to competitive service providers requires laborious and error-prone manual patching and repatching of end-user ports. AFS allow the wholesale muni or utility to connect customers to any service provider without any manual intervention. When an end user chooses to switch to a different service provider, the end user port can be remotely physically switched to the new service provider. The home run architecture has the highest initial fiber related capital costs, but permits unbundling of both the physical plant and the logical layer. The home run architecture therefore supports a per subscriber choice of data link layer services using unbundled network element based competition, as well as competition in upper layer voice, video, and data services using open access. A medium-sized city's greenfield FTTX network deployment can cost $21 million, which includes outside plant construction labor, materials, engineering, permitting, and pole attachment licensing. This estimate assumes the city constructs and owns the FTTX infrastructure up to a demarcation point at the optical tap near each residence and business, and leases the dark fiber backbone and distribution fiber to a private partner. Because this estimate does not include any electronics, subscriber equipment, or drops, it is referred to as the dark FTTX cost estimate. It is especially relevant if a muni or city opts for a partnership model in which it is responsible for constructing the physical network and a service provider partner lights the network using open access provisioning. Next slide, please. In a manual connection approach, mistakes occur due to discrepancies between the actual physical settings of the connections and their management because these processes are independent. Many cross-connects in a fiber cabling system are done manually by muni techs. So AFS is a critical component to a viable long-term business plan for munis and utilities. Strong operations, administration, maintenance, and provisioning, or OAM&P capabilities, offering end-to-end service management is also required. AFS network management is based on direct interaction between the network element and an OSS using an element management system. This approach is well understood, especially in terms of OSS integration. For example, delivering a robust solution that is easy to manage and troubleshoot is feasible with Wave2Wave's AFS element management system. The EMS provides for efficient and automated operation while reducing Opex. This SNMP management system provides configuration, performance, network assurance, and provisioning functions for Wave2Wave's Roam AFS system. The EMS is based on the industry standard Telecommunications Management Network, or TMN, architecture and features open systems and a hardened infrastructure to support high-performance large application solutions. AFS equipment also requires high optical performance such as low insertion loss, high return loss, and transparency at optical wavelengths. Moreover, the optical connection should be self-holding even if the power supply is cut off. This is critical for seamless FTTX test integration. Next slide, please. There are more than 30,000 COs in North America, and the PSTN remains a $100 billion annual revenue business in the U.S. alone. So increasing automation is a strategic goal for telcos to lead them into the next evolution of value-added services. Opex savings can also result from testing multiple PONs with the same OTDR using an AFS to select the PON to be tested at the CO. This approach enables a single OTDR to handle testing for an entire CO. New fibers being installed can be connected to an OTDR or light source in the CO. A technician arriving at the manhole or street cabinet where the fibers are to be terminated then instructs the NOC to connect the visible light source to a given target fiber, enabling the field tech to immediately identify the fiber. Cycling through this process allows the technician to complete the task quickly and accurately. The AFS may also be used to connect OTDR test equipment in order to characterize each newly installed fiber. When an outage does occur, AFS can be used to perform remote troubleshooting by connecting the affected fiber remotely to an OTDR to quickly locate the fault. Technicians can then be efficiently dispatched directly to the location of the problem fiber. Next slide, please. Opex savings can also result from testing multiple PONs with the same OTDR using an automated optical switch to select the PON to be tested at the CO. This approach enables a single OTDR to handle testing for an entire CO. The slide shows how to use this centralized approach. Technicians can log into the application from their mobile phone. After registering the customer ID, technicians enter the optical power measured at the customer connector, which triggers an OTDR measurement. The system automatically recognizes the new peak and records its position and level, and subsequently stores the information in the OSS records. Typically, PONs are installed in two segments by two different groups with different testing requirements. The first phase is the installation of the feeder cable from the CO to the splitter. This segment is typically installed by a contractor and is certified after installation by measuring the total loss and evaluating splices and connectors. This segment requires a PON-capable OTDR with high dynamic range. The second last mile segment runs from the splitter to the ONT. Testing during installation and maintenance typically requires a fault location, connectivity check, and isolation. The highly capable instruments used to certify the feeder cable are not required for testing this segment, and so it is possible to use a less expensive and more user-friendly drop cable fault locator. Additional benefits of this approach with seamless AFS integration include remote location access to the PON test through a web browser or mobile phone. A single person can test the network during installation and quickly and easily distinguish problems between the PON equipment and the fiber. Next slide, please. In FTTX networks, AFS enables the service provider to remotely configure connections without risky manual patching and without exposing live connections to human error. Remote access to the physical layer also enables a network characterization testing, troubleshooting, and fault workaround to be performed from the Network Operations Center. Staying competitive and ensuring long-term profitability are two crucial drivers for today's telco. To ensure their profitability, telcos must optimize their networks and carefully control both capital and operational expenses. Positioning the AFS at critical flexibility points allow just that, while also improving quality of service by offering a number of critical capabilities, including remote troubleshooting of problem fibers, central monitoring of service degradation over time, rapid fiber identification, cost-effective protection, and accurate connectivity records. Additional benefits of automated fiber switching as an integral PON ecosystem component include faster time to revenue via reduced provisioning times, increased customer satisfaction since service turn-up delays are minimized, fewer truck rolls leading to direct labor savings, sharing of centrally located test equipment such as OTDRs, and as noted earlier, efficient use of central office space and power utilization. AFS also significantly reduce other equipment capital expense needs while reducing operating expenses, delivering a return on investment in less than 2 years. Next slide, please. We have demonstrated that automated fiber switching enables a more efficient services provisioning and test approach. It reduces the amount of OLT line cards needed while closely matching capital expenditures to service turnup. The result is significant CapEx savings. Automated fiber switching products also significantly offset capital expenses of OLT line cards while simultaneously reducing operating expenses. This can deliver a return on investment in less than 2 years and improve the FTTX business case. A great example is Wave-to-Wave's Roam system, which enables physical fiber connections to be made automatically, remotely, quickly, and without on-site manual intervention. The Roam product is about network connections, when needed and where needed. With patented mechanical latching technology and fiber management, making connections is possible remotely, precisely, and robotically. Roam reduces CapEx and Opex by automating fiber management. The Roam product allows telcos, munis, and utilities to remotely configure connections without risky manual patching and without exposing high usage connections to human error. So in summary, the only effective way to manage FTTX costs is to minimize equipment and labor requirements. Specifically, it is imperative to minimize the need for stranded OLT equipment. Therefore, automated fiber switches such as the Roam product line should be a key ecosystem component in the telco arsenal to address PON economics and ongoing operations concerns. This brings us to the end of the webinar. Thank you for joining us today, and we look forward to seeing you on another webinar in the series. And please feel free to send any questions you may have to info@wavetowave.com. Have a great day and see you soon.